Good morning, everybody. Thank you all for attending class yet again. Today we are going to continue our discussion in friction. This time today we're going to be looking more specifically at turbulent flow and how we can incorporate skin friction as well as other sources of friction into our energy balance expressions. So, without further ado, let's talk about friction and turbulent flow. Oh, looks like somebody's got a video going. So, in turbulence, or in turbulent flow, a very thin boundary layer exists between the wall and fluid flowing in our system. Such that as if I was to draw a comparison between laminar flow, which we talked on Monday, having this parabolic profile, and then comparing it to turbulent flow, we would find that they have two very differing flow profiles. And so what this tells us is that in turbulent flow, the velocity distribution is more even. What we find based on that is that the friction factor that we use to determine our frictional dissipation will be much lower in turbulent flow as compared to laminar flow. However, our frictional dissipation in turbulent flow will be greater in laminar and turbulent flow as compared to laminar flow. And so what we find when we're looking at a comparison between laminar flow and turbulent flow now, could anyone remind me what the expression we had developed on Monday for laminar flow is called? Anybody?
16 mu over rho u d.
That was one of the expressions. It was what I'm referring to is when we discussed identifying this expression, which was the Hagen-Poiseuille. When from the Hagen-Poiseuille, we find that friction is directly proportional to fluid velocity times its viscosity. So there's a linear dependence in friction on velocity and viscosity. However, in turbulent flow, friction becomes proportional only to velocity, but to the square of the velocity. Meaning changes in velocity or increases in flow rate have a much more dramatic effect on frictional dissipation in turbulent flow as compared to laminar flow. Another thing that we have to consider when determining frictional dissipation and surface roughness, and our friction factor is surface roughness. Surface roughness describes the relative tendency for shear to exist on, or I should say at, the solid fluid interface. And so what we find is that we have to define a value for surface roughness, which is usually done as a K. Some books do it as an epsilon. And this tells us a little bit in terms of what we can expect to happen in terms of shear stress at that solid fluid interface. And the units of surface roughness are units of length. So you're going to see feet or meters to describe surface roughness for various materials of construction. And so just kind of as an example, I'll switch it over so you can kind of see some examples of a roughness parameter. So for steel, you're going to see commercial steel, stainless steel. That's probably the most common that we see when we look at systems. It's going to be 0.00015 feet. Civil engineers, and they're looking at flow and friction dissipation in their systems when they consider maybe concrete type flow. They're going to look at 0.01 to 0.01 feet. And extremely smooth systems like PVC, copper, and brass, they're going to have a much, much lower surface roughness. And so with these values in mind, what we end up calculating is known as a relative roughness factor, which is simply the roughness factor K over our pipe diameter.
You're still showing the PowerPoint.
Oh, thank you. Our relative roughness, which is simply our surface roughness over the pipe diameter. And what we'll find here is this is unitless. And with this parameter, we can identify friction as a function of both our relative roughness and our Reynolds number as it applies in turbulent flow. So with these two values in mind, in turbulent flow, we can find our friction factor. And so the question then becomes, how do we do that? Well, the way we do that is through the use of a handy dandy chart, which is known as the friction factor chart. Now for this class, what we're going to be using is this fanning friction factor chart, which if on the x-axis, what we see is a logarithmic plot of Reynolds number, and on the secondary y-axis, we see a relative logarithmic plot of relative roughness. So to identify your friction factor, what you do is you calculate your system's Reynolds number. Then with that in mind, you look for the intersection of the Reynolds number and your relative roughness value. Once you find that value or that intersection, you can then go over to the primary y-axis to find your friction factor. And with that in mind, with the friction factor, you can then calculate your pressure drop by the expression we developed on Monday, or if you're looking for the friction term itself, you can calculate it as such.
You're still on the PowerPoint.
Thank you. I'm sorry, I'm going to be bouncing a bunch today. Never hesitate to call me out. So with that friction factor, you can calculate the expected pressure drop due to the skin friction, or if you're looking for the frictional term itself, you simply divide by diameter, or excuse me, by density to get your frictional dissipation. Does that make sense, or are there any questions or confusion that I can help clarify? Just as a quick recap before you guys ask those questions, just the biggest thing is to understand is this implication of laminar versus turbulent flow. When you're looking at laminar flow, you have a linear dependence of both fluid velocity and viscosity. In turbulent flow, the dependence on viscosity falls away, and you're more looking at a dependence on the square of the velocity. And so when we look to define friction in turbulent flow, we rely on a relative roughness value as well as our Reynolds number using a friction chart to then find our friction factor, which can then be used to calculate both pressure drop and friction. So any confusion, any points that I can clarify?
I was going to ask, what if it was a problem we are given the Reynolds number, but not a value for the relative roughness? Because I noticed on the chart, all the values required a roughness value, but I didn't see a line there for it in case we could assume it was a smooth pipe.
In these problems, most often than not, I would assume either a smooth pipe or a stainless steel pipe. I'm pretty sure on the homework because I've specified, but if you ever have questions like that, I'm always happy to clarify on problems. But here, I'll see if I can switch it back over to the chart. So if you see on the chart here in the bottom left, there's various materials that they've got, where you see smooth, which the smooth line is essentially the bottom curve in this chart. And the most common materials are also shown. Most often than not, we're looking at steel or smooth pipe, because in chemical engineering, you're rarely going to consider some of those other materials, maybe galvanized iron, but you're not really going to be looking at concrete very much in this class, if at all. And so we typically stick to stainless steel because that's kind of what ends up most common in piping sins. Either that or PVC type systems, which are considered smooth. One other thing I do want to point out is this system, as we've been discussing, falls under this category that is known as looking at friction factor by the Fanning friction factor method. There is a second method, which is used in other textbooks. Why there's two methods, I'm not sure, but it's called the Moody friction factor. And it's the same approach. However, some of the variables and mainly the constants that are expressed in this method are a little different. So you'll notice that the friction factors that are calculated in the Moody values system is much higher than what's in Fanning. And you'll also notice, we talked about for laminar flow, the friction factor is simply 16 over the Reynolds number. The change in variables results in a slight difference in this system, so it ends up being 64 Reynolds number. So it's just kind of a be careful in terms of which method you're going to use. For this class, we're really going to stick to the fanning friction factor method. However, the Moody is also used in in applications. And if I'm honest, it really doesn't matter too much which. It's just, you know, people's personal preference and how they've been taught. One could argue the Moody is a little bit more common, but the overall methods are the same. It's just slight changes in how the equations are derived, but you end up with the same values in terms of frictional dissipation at the end. So I just want to, I put it in there to kind of, you know, bring that in mind, just in case you're ever in industry and you're like, oh, we use the fanning friction, and then someone's going to say, what's the fanning friction? And you can kind of see it and explain it. All right, with that in mind, are there any further questions or points of clarification that I can make? If not, let's take a look at an example. So for this example, we can consider 20 gallons per minute of water, which enters a 100-foot, 3-inch Schedule 40 stainless steel pipe at a pressure of 45 psia. What is the pressure drop that we can expect across this pipe or flow section? All right. So let's take a look at this example. So for this system, our flow rate is 20 gallons per minute, which if we wanted to convert to cubic feet per second, we could divide 7.48 gallons in a cubic foot. And in 1 minute, there's 60 seconds. So for this, we find approximately 0.045 cubic feet per second is our flow rate. Our pipe diameter is 3 inches of Schedule 40, which is 3.068 inches, which is approximately 0.256 feet. We see that we're looking at water. So the density of our water, 62.4 pound mass per cubic foot. And it also specified that our inlet pressure is 45 psia. So in order to determine our expected pressure drop due to skin friction, we're going to need to know both the Reynolds number and our relative roughness value. So I typically calculate my Reynolds first, rho UD over mu. So the density of water being 62.4 pound mass per cubic feet. The velocity, which is going to be our volumetric flow rate over our area, or 0.045 cubic feet per second over our area, which for a 3-inch Schedule 40 pipe, the area is approximately 0.0513 square feet, which fortunately we can find from our textbook. Which if we do that calculation, we have a velocity of approximately 0.88 feet per second. So we have 0.88 feet per second, our diameter, which we had 0.256 feet, over our viscosity, which the viscosity of water is 1 centipoise. which in English unit is approximately 6.72 times 10 to the minus 4 pound mass per foot second. So if we calculate this Reynolds number, we should get approximately somewhere on the order of about 20,000. Let me do the calculation real quick. Yeah, so about 21,000. And what I'll say for these types of problems is you don't have to be super exact about the Reynolds number, primarily because when you're looking at that log plot, there isn't a whole lot of figures really present in that chart. So I ended up with 20,918, which tells me the Reynolds number is somewhere on the order of 21,000. So with this, I can then calculate our relative roughness, which our K over D value for stainless steel, the K is 0.00015 feet. The diameter, I already said, was 0.256 feet, which gives us a relative roughness value of approximately 0.00059. So now we have our Reynolds and our relative roughness. So if we jump over to our figure, what would you say would be the Franning friction factor for this problem? And here I can zoom in for you guys a little bit, provided my computer doesn't get mad at me for it. So what would you identify as the friction factor? Nope. And this is where it helps to have like a straight edge, especially if you got your book using that, that really helps. So anybody want to take a number?
.0046.
All right, so we got 0.0046 would be somewhere here. So let's take a look. So 21,000 is around 2 times 10 to the 5. So we're looking at 0.006, which would be about here. So 0.0046, that looks pretty good. So somewhere between 0046 and 0048 would be probably really good. So I appreciate the participation. So let's jump back over and we'll use that value to finish our calculation. So we have F is approximately 0.0046. And with that in mind, we can now calculate our expected pressure drop by this expression. So 2 times 0.0046 times the density, 62.4 pound mass per cubic foot, times the velocity, which we found was 0.88 feet per second, squared times the length, which is 100 feet, divided by the diameter, which was 0.256 feet. Now to get it to PSIA, we also have to divide by G sub C, 32.2 pound mass feet per pound force second squared. And then we also have to divide by 144. If we do that, we should get a pressure drop of approximately 0.05 PSI, which isn't too terrible at all, keeping in mind it's only about 100 feet. All right. All right, the next thing that we can consider are additional sources of friction. Which for this class is going to fall into one of three categories. And those are expansion losses, contraction losses, and fitting losses. Now, when we're considering expansion losses, that is in systems where we're looking at flow moving from one section with a certain diameter as compared to another section with a different diameter. Should probably call that a different letter. And so what we find is our fluid isn't going to get to this flow section, realize that there's no space, wait for a red light, take a left turn, and do this. That's not how the flow is going to work. You know, from our previous discussions in momentum, what's more likely going to happen is there's going to be a fanning effect as the fluid enters that section. So the velocity profile is going to look a little bit more like this, right? And since the area is larger, the velocity is going to decrease. And so what we find is the fluid can't essentially immediately fill this void space. And so what ends up happening is what you have is vortices or eddies emerge in these zones. And what that ends up doing is removing energy from the fluid by essentially an increase in turbulence and energy dissipation due to all the added shear that we see happening by these eddies on the walls or in the interfaces. Oh, that is not what I wanted to do. And so we can quantify that energy dissipation as a form of friction loss, which we can denote H sub E, which is equal to KE times U squared over 2, where KE is a coefficient of expansion, which can be approximated by the expression 1 minus A sub A over A sub B squared. And so, with an expansion loss coefficient, we can then multiply it as a function by the kinetic energy of the fluid, as denoted by U squared over 2. And that gives us our correlation or our correction in terms of friction loss due to expansion losses. Now for contraction, it follows a similar principle, just kind of when you're thinking about it in the opposite. Now you're going to have fluid flow. Oh, I liked using blue. I'm going to change it. And once again, it's not going to realize there's a wall, you know, turn on its turn signal or not, and, you know, take the left. It's, you know, as much as we'd like to think that fluid is intelligent, it's not. What's most likely going to happen is there's going to be a compression effect. And at the same time, the fluid that strikes these dead sections are going to end up with vortices and eddying occurring there to, one, further dissipate energy, increase of shear at those edges, and it's also a natural result of the compression that exists in those flow sections. And so what we see is if we denote this A, we denote this B, we find a similar expression for contraction losses, H sub C is equal to KC U squared over 2, where our contraction coefficient is 1 minus area of B over area of A. And so by identifying our contraction coefficient, we can then calculate our expected frictional dissipation due to fluid contraction. So we have, go ahead.
I was going to ask, I noticed that for KE, it was the value was squared. Is that the same for KC?
It is not the same for KC.
Okay.
No problem. Any other questions? That's a good question. And yeah, it does seem a little unexpected that the contraction losses aren't. Oh, but I did forget, because I can't see my notes completely, there is a factor here for contraction. Thank you for that question. I would have missed it. It's 0.4 times 1 minus AA over AB. And here, I'll tell you what, I'll just clean up the whole expression. So yes, the expansion has a square in the expression. The contraction does not, but there is a essentially factor of 0.4.
Thank you.
Of course. So we have expansion and contraction. So the question then becomes, what about fittings? Well, fittings has a similar approach where you have KF times U squared over 2, but the correction factor for fittings is a little different in that there are so many types of fittings that exist in a flow system. It was much easier to do empirical experiments and then correlate the fittings themselves with a KF value, which means most fittings, if not all fittings, are going to have some form of KF that's reported in its specification sheet. And so depending on the system, in order to find losses due to fittings, all you really need to look at is the reported fitting coefficient. So for example, a 90 to 45 degree elbow is going to have a fitting coefficient of 0.35. A half open valve is going to have a fitting coefficient of 4.5. And like I said, it's going to vary from fitting to fitting, even from manufacturer to manufacturer. And so when you're considering energy and kinetic losses in fittings, tees, things, all those kinds of things, you have to essentially look them up. For any sort of midterm, if you're going to see this, I would provide you the table that you would need to obtain the fitting values.
I'm assuming that there isn't a table in our textbook.
There is a table in your textbook. This is actually taken from your textbook. This is table 5.1 on page 124. And so, with that in mind, so for KF, see table or Google. I should say table manufacturer.
You're on the PowerPoint.
Thank you. Or Google. So we have, when we're recapping, we have expansion, contraction, fittings, and skin friction as our key sources of friction in our fluid flow systems. So if we were to determine F for our mechanical energy balance, we would write an expression that combines each of these sources of friction into one expression or one equation. And so what you'll notice is that each of these systems is directly related to the kinetic energy that exists within our system. So more often than not, we can write the expression as such. And here I'll space it out for legibility sakes. And if we wanted to write it in terms of head loss, we could also write it in this form. So these become extremely important expressions for determining our frictional dissipation in our fluid flow systems, which denotes what we expect due to skin friction, which is more often than not going to be the most predominant source of frictional dissipation, and then as well as any expansion losses, contraction losses, and fittings within our system. So with this expression, now when we're looking at energy balance calculations and solving for power, we don't have to neglect friction any longer. Isn't that exciting? So let's take a look at an example of this. So now let's say we've got water being pumped from a reservoir to the top of a hill through a 6-inch Schedule 80 pipe at an average velocity of 2.2 feet per second. The pipe discharges into the atmosphere at a level 330 feet above the level of the reservoir, assuming the pipeline is 1,100 feet long. If the overall efficiency of the pump driving flow is 70% and the cost of electricity is 7 cents per kilowatt hour, what is the hour energy cost for pumping the water? So this is kind of a fully fledged mechanical energy balance for fluid mechanics problem, where you have to develop your mechanical energy balance, identify the pertinent variables that can be neglected and which must be calculated to solve for your work. And since we have to include friction, we also have to calculate the source of friction and incorporate that into our work calculation, which then with that in mind, we can solve for power. And so on your homework this week on that synthesis assignment, when I've asked you to develop a flow chart to solve particular problems, this is the type of problem I have in mind, particularly these fully fledged mechanical energy balance problems with friction included. All right, so let's see with the rest of class today if we can get through this problem together. So first things first, the one thing I always like to do is draw the problem. So we've got some form of reservoir, some pumping system, and it's taking it, to Mordor and back to another reservoir. So it gets discharged. So it says it's being lifted 330 feet. The pipe length is 1,100 feet. The velocity of flow is 2.2 feet per second. It's a, 6-inch Schedule 80 pipe. So it's a pretty honking pipe, which means the diameter is 5.761 inches, which is approximately
0.48 feet.
Thank you. And it also means the area of flow from the book Luckily, they have that directly, is 0.181 square feet. What else do we need to know? The efficiency of the pump is 0.7, and the cost of electricity is 0.7 cents per kilowatt hour. So in this problem, as in all other problems, the first thing, once you have the problem written out, the variables identified, you're going to want to create your energy balance. So which terms can we neglect in the energy balance expression?
Pressure.
Pressure.
Yeah, I haven't said anything about pressurizing the flow. So in that, I would consider both the starting end pressure to be about atmosphere. And a lot of times in these types of systems, you can always work it into the static, the lift that you need to incorporate into the fluid. And so with this in mind, I can further expand this out. So once again, I'd probably also consider this initial velocity negligible for a couple of reasons. One, if you consider it to be not negligible, this term will cancel, and you may run into a tendency of underestimating your power requirements. However, at the same time, a lot of times in these energy balance expressions, you'll find that friction and the lift are going to dominate the kinetic energy term in these calculations. So sometimes neglecting it won't hurt you, but the more conservative estimation in terms of work and power is to always just consider the energy required to get it moving, the energy required to lift it, and the energy required to overcome any shear and friction that happens during transport. And so we're left with u squared over 2 plus g times our delta z term plus friction equals our work, which is negative.
Can't we cancel out Z1 though?
Yeah, we can, if you want. But like I said, at the end of the day, in terms of how you do it, the Z2 is going to be 330 feet, or the delta Z is still going to be 330 feet. But that's fair, depending on how you pick those points. All right, so this is
quick
1,
question.
this is 2. Yes.
Which was, if you scroll down to your most recent equation, you
Yes.
set work on the other side to be, is that positive or negative? Because I think it would be negative if you're subtracting it to the other side.
Yeah, the work is going to be negative. That's what that little line there is supposed to exemplify. So we have our velocity squared term. We know what gravity is. We know what our delta Z is, or our Z2. So the issue is we need to find our friction, which for this system, we're just going to consider skin friction, which means our friction is going to be delta P over rho, which is equal to 2F U squared L over D. So in order to find friction, we have to find our friction factor. So we need our Reynolds number, which is rho UD over mu. So we're looking at water flowing through a system. So the density is 62.4 pound mass per cubic feet. The velocity is 2.2 feet per second. The diameter is 0.48 feet. And the viscosity was 6.72 times 10 to the minus 4 pound mass per feet second. So if I do this calculation quickly, I get approximately 98,000. For a Reynolds number. I didn't say what type of material, but I'm going to assume it's stainless steel. So my K over D is going to be 0.00015 divided by 0.48 feet, which gives me a relative roughness of approximately, my calculator would behave, 0.0003. So with that in mind, I'll jump over to our friction chart. And so I'm looking at 0.0003, which is going to be somewhere between 004 and 002, and 98,000, which I would just consider it to be 100,000, because like I said, this isn't as accurate as we all like to say. So I'd probably put it somewhere right around here. If my mouse says to.
0.0045.
I would call it 0.0039.
Why are you looking at 10 to the 5th, though?
This is 10 to the 6th. Oh, it is 10 to the 5th. Sorry. So we're looking at what, 98,000, which would be 100,000, so 10 to the 5th. So 0048. Yeah, about 0.0048 would work. So now that we have our friction factor, we can then solve for our friction value.
We're on PowerPoint.
Thank you. So F is going to be delta P over rho, which is going to be 2FL U squared over D. So we have 2 times 0.0048 times 1,100 feet times U squared 2.2 feet per second squared over D 0.48 feet. So I end up with doing this calculation, F to be approximately 1,064.8 feet squared per second squared. So now that we have friction, we can go back to our energy balance and solve for work. So we have 1,064.8 feet squared per second squared plus 2.2 feet per second squared over 2 plus 32.2 feet per second times the lift, 330 feet. So then work is going to be a negative pretty big number, 11,000. Actually, we don't even need the decimals. Feet squared per second squared. So then to solve for power, once again, mass flow times work over efficiency. The mass flow rate is the density, 62.4 pound mass per cubic feet, times the velocity, 2.2 feet per second, times the flow area, which for a 6-inch Schedule 40 pipe was 0.181 square feet. So then we add the work, 11,693, and then we divide by the efficiency. Last thing we have to do though is convert because we have to put it in pound force. So we would divide, I'll put it over here, 32.2 pound mass feet per pound force second squared, and then divide it once again by 550 pound force feet per second per horsepower. And this will give us our power in horsepower. Which ends up as a massive pump, 23.4 horsepower. Which if I was to convert to kilowatt hours, or excuse me, kilowatts, I would get 17.45 kilowatts. So the question is, how much would it consume in terms of hourly energy costs? So if it's the power requirement is 17.45 kilowatts, and an hour, it would use 17.45 kilowatt hours, which means the energy cost would just simply be the 7 cents in terms of dollars per kilowatt hour times the 17.45 kilowatts per hour, hours per hour, which gives us our final value of $1.22 per hour in terms of cost to run the pump. So I know I kind of rushed through there at the end, but if you have questions, I'd be more than happy to answer them. And on Friday, we're going to work on a couple more examples incorporating some fittings and expansion and contraction losses. So is there anything I can clarify or reemphasize for you all?
What did you say the fanning friction factor was?
I ended up with 0.0048.
Thank you.
Another question I meant to ask was, is that table where you, or the chart where we found the fanning friction factor in our book as well?
Yes, it is. It is figure, I believe, 510 on page 115 of your textbook. I apologize. I should have mentioned that earlier. Any other questions? All right. If not, that's all I have for you all today. I hope you all have a great day. If you have any questions, feel free to reach out to me in email or in office hours. Take care and have a great one.
Thank you.
Thank you.
Thank you.